Okay, so here we are back on the dashboard of our Excel spreadsheet. The dashboard is where we're going to input our whole design. So the teal colors are what we control. And what we do is we fix the chemistry and we fix whether it's a hybrid or an electric vehicle. And that fixes, then we can go to these array of 7 other variations besides, so these are all fixed chemistry, fixed electric vehicle. Then you can do 7 variations below that. So that's how this is designed. And we're going to also look at how we can use this and apply it to the Ferrari plug-in hybrid or the Rivian EV batteries. So let's start off with this EV battery, and we're going to choose the high nickel version, the highest nickel version, because that has the less cobalt, because that's the one desire trend in industry is to minimize cobalt because of its cost, scarcity, and humanitarian challenge with getting a steady supply. Okay, so we're going to apply this to an electric vehicle. Then you can actually include a charging specification. So we need to do that because, or we don't need to do that, but we should, because it's relatively easy here. If we click yes, it's gonna open up another control, another blue box for the charging time. Okay, so let's go. So there's some defaults built in. I haven't changed this from the fresh default setting it comes in. And what it does, it has an array of 7 batteries to analyze. There's going to be 7 different calculations for the fixed chemistry and EV. So it fixed them all at 300 kilowatts. And it's going to use defaults, a lot of defaults built in, which is nice. Let's just leave that. Then you can either specify, you're going to specify capacity. They give you an option of 2 different units. These are the same thing. It's the same joules, except you just get joules a different way. So it's either the current that it gives over certain hours, that's coulombs, and kilowatt hours, that's joules. So they're both related to the capacity. It's just 2 different ways of saying it. So the way they set it up by default, they said every battery on this array of 7 is going to be 100 kilowatt hours. Okay. Then by default here, they said it's going to take 1 hour to charge. And then we could specify that and as we go along. So let's go ahead, let's leave that as default. Then what they did for this array, what they have done was to pick 7 variations of module sizes, basically. I mean, the battery size itself. So it says they're all going to be either 12 cells per module or 20 cells per module. Then this number of cells, number of modules, number of rows, this basically controls the size and footprint of the battery. So if you make you add more modules and you add more cells, that gives the battery more capacity. It's going to charge. It's going to have a more charging capacity, and it's also going to control the voltage, and it's going to control the size. So these variations here are different iterations that do 3 things: changes the capacity. Okay, and then if the capacity is fixed, which is it is fixed here, it's going to change the voltage. So the way I suggest to do it is just to fix the voltage here. I mean, the wattage. I'm sorry, the capacity. Here it is, capacity. Fix the capacity here. Fix the kilowatts here. And then what this is going to do here, it's going to do 2 things. It's going to change the size, physical size of the cell, and it's going to change the voltage, operating voltage, because they're all coupled here. The amount of power you're fixing, and the kilowatt rating you're fixing, and the capacity the kilowatt power and the kilowatt power and the kilowatt hour. I didn't realize that rhymed. Kilowatt hours is capacity. We're going to fix that. The power, which is in kilowatts, we're going to fix. Then when we change these here, it's going to change the size of the battery, and it's going to change the voltage of the battery. Okay, so let's leave this. So this is the default. The only thing I've changed in this from when I first opened it is I changed it to a high nickel, the highest nickel in this spreadsheet, and I changed it to EV, and I changed it to calculate the charging requirements. Then once I selected the voltage requirements, it opened up this blue row here. And then, so I haven't changed anything yet. What's built with this default numbers that's already there, it's that it keeps those numbers here, and then the only across the 7 batteries, and then the variations across these 7 batteries that's built in the default is the size of the cell of the pack, and that's going to control the voltage and all these other things based on just these variations here. Okay, so let's go down the dashboard more. There's no more teal until you get to this number of manufacturing packs per year. This is pretty much the production rate, the annual production rate. And 500,000 packs is probably a decent number for Rivian, because they plan to sell they plan to manufacture around 100,000 Rivians per year or something like that. We can look that up easily. Forget the number, but so that's the amount. They definitely each Rivian needs 1 battery pack, but of course it's there's always a whole market for spare packs and maintenance and things like that. So some multiple of the number of Rivians that are planned to sell is how many packs you need per year. So let's leave that at 500,000 for now. Then there's these other manufacturing options. We'll leave those as well. And here are the results. All the teal is done. There's no more inputs. And then it gives you a good starting point to try to look at what the results are from those inputs we had. And green is good. It says that there's no errors. There are warnings. And there's a nice little table on the right for battery 1 has 1 warning. But besides that, battery 1, if we go down this column for battery 1, there's no errors on the calculations. The plant size for 500,000 per year corresponds to this amount of gigawatts per year, gigawatt hours. Power to energy ratio, it is green, meaning that it's not a crazy aphysical design. It has the cooling is good enough, and there's no problems with the cathode thickness. That it is going to have some limitations, but there's no error, and it has the capacity we need. So all of these greens are here. There's just this 1 warning. So let's go to the key here on the side. So warning 9 says that there is no input charger power that exists to get a 60-minute charge. So that's what that warning is. They said it can be done according to the circuit of the battery, but you can't really find a charger to take it that fast. Okay, so that's just a warning. But the rest are good. You can get a charge within 60 minutes. Okay, so going down more, these are just ways to plot. This little table here might be useful. I wanted to see other things. So what you can do is if you click on this blue thing, it'll open up a menu arrow there, and you can plot this XY graph for XY, and then you can do the second axis on the right. You can have red symbols to belong to this axis, blue symbols to go to that axis, and you can choose to plot different things against each other. And I wish it had total cost. It has total energy capacity. That's good. That is good, but and then it has cost per kilowatt hour. Okay, it has cost per pack. That's good. So let's plot cost per pack against total energy. Yeah, total energy against, let's see, maybe the volume. This is the size of the battery. The weight's probably also important, but you'd also want to have a huge battery. Yeah, so across these 7 array of batteries, pretty much I left it alone. All of that array is doing is varying the size and dimensions of the battery. In terms of the physical space, we fixed the energy. We fixed it at 100 kilowatt hours. That was fixed. We could have changed it if we want, but we fixed it for all 7. And it's going to have a range, pretty close range, $10,000, give or take, or like, let's say $10,500 plus or minus 200. That's the range in cost. And the volume's not going to change too much. Actually, yeah, the volume goes maybe like from 260 liters all the way up like 1/4 to 300. So that's the biggest effect. And so, yeah, that it answers a lot. Okay, so that, okay, yeah, so now let's go to summary of results tab here. Summary of results. Then you can pull out each of these answers more directly as well without having to plot it. You could also just pull these numbers out here. It gives you the capacity that we already fixed that, but then it gives you the results here. And I'll go down the list of this PDF and show you where to find these numbers. So a lot of them will be here in the summary results, and a lot of them will be on manufacturing cost. So this is the manufacturing cost tab. And then when you go to the manufacturing cost tab, if you go down, this list has a lot of detail, which is nice, but it's all built in. A lot of built-in assumptions that are pretty established in the industry now. Okay, so here's the assembly cost and stats. These are performance of the manufacturing processes. And then let's go all the way down to summary of battery system cost. Or here, above this, what is this called? Calculation of pack cost. This is super useful because A, it tells you how much is a total investment for this. If you're going to make 500,000 packs per year, this is how much building space you need and so forth. And then they assume some cost. We just go with the defaults here. This is the cost of building and land, 600 million or so. The bottom line is that to build this manufacturing plant, according to battery 1 specifications, it's going to cost $5.2 million for battery 1. And for this whole array, there is some variation in this plant cost. So for let's say our final design is battery 1. Our initial total investment is 5.2 million. The variable cost, total variable cost per pack is almost $8,000 per pack. The fixed costs are $1,400 per pack. So the total cost per pack. So this is the fixed and variable cost here. Variable is per pack, and then we could also say $1,400 per pack, and we can multiply it by 500,000 target that we specified at the beginning. That will give you a true fixed cost, because fixed cost should be fixed. It doesn't depend on the amount of packs. Yeah. So that's basically it. Now I'll show you how this corresponds to the battery, the PDF we're talking about. Okay, so I have I'm looking at the PDF on my computer, but I'll keep the screen share on the dashboard. So let's go down this list of the assignment. Okay, so what we chosen, let's go up to this dashboard. Starting from the top, choose one battery to propose. While we chose an EV, I'm going to choose the max pack. So I want a super long range. And we're going to choose the NMC Cobalt battery pack. So the section 1A, first bullet point, what is the capacity, power, and voltage of your proposed battery pack and why? Okay, so the capacity is going to be corresponding to the Max Pack Rivian, which is going to have to correspond to 400 miles. So let's see if the miles are directly here. Default requirements. So the miles are not here because you can't really get the miles directly from the battery design itself. That is an indirect relationship because it depends on the car, what you're doing. So we can get a starting point from the fact that the Rivian standard battery claims to be 260 miles under 135 kilowatt hours. If we want to, we're not double. If the max pack goes to 400 miles, let's see, I can do that right now. 400 divided by 320. Oh, sorry. 400 divided by 260 is 1.5-ish. Okay, so let's say that instead of 135 kilowatt hours, it's 1.5 that. So let's go for a capacity of about 208, or let's just say 200. So based on this extrapolation of the standard battery, which is going to be a different chemistry, but just as a good starting point, as we're going to assume that this battery, to go to this extended 400 miles Rivian, extrapolating from the standard, let's say it's going to need 200 kilowatt hours. Let's go a margin of safety. Let's say 220. 220. Yeah. And let's do that across this whole array. All of these, we're going to analyze all of these as 220. That's going to be the max pack capacity. So let's just fix that in, just to get some numbers. So the capacity is going to be 220 kilowatt hours. The power, it's going to be, let's keep it at 300 because the it needs to be, it's a full electric, so it can't be like a supplement. It's basically the default here for a reason, that it's a good round number for a full electric vehicle because it needs to be, it's not going to be a super, I mean, a hybrid level. It needs to be more performing than that because it's the whole car's powertrain. So let's go ahead and leave it at 300. We can look it up, and for what you see in the other electric vehicles, this is a good ballpark kilowatts for a car. It also, and it's no accident that this is a combustion internal combustion engines operate around this amount of kilowatts or horsepower. Okay, so let's leave it at 300. We specify this capacity here. Let's also leave this 60 minutes to charge. Seems like a long time. It is, and let's just leave that as a default. I mean, it's a long time compared to gasoline fueling, but it's standard for electric vehicles. Let's leave that. Now this array here is going to control both the size, the footprint of the car, the volume taken in the car, and because we fixed the other things, it's going to determine the voltage, operating voltage. So now that we did change a couple things, let me do Control Shift R really quick to make sure it calculates, keeps these calculations going. Okay, so we fixed the capacity, we fixed the voltage, I mean the power. What is the voltage? Well, to get the voltage, you have to go here, summary of results, and it is here. Where's the voltage? Yeah, here, 4. I mean, this cell here, there's number 4 here is because there's a table here that populates. But we won't worry about this table. It's kind of overwhelming. I'll show you exactly where it is. It's here. So after inputting all that stuff, we fixed the capacity across the 7 batteries. We fixed the kilowatts across the 7 batteries. And then by default, there's these array of number of modules and number of rows in the number of cells, and then the number of rows and the number of columns. That is gives you a certain volume size of your cell, and then that gives you a certain voltage once you put those all together. So the biggest the highest number of rows and the highest number of columns will give you the highest voltage. So this is the voltage here. So we're not at 800 volts. The Rivian electric vehicles are going to design to be 800 volts. So let's find a battery to try to make it 100 volts, 800 volts. This one is high. That probably means it has the largest volume. So yeah, I'll go ahead and go down this summary of results here. Not necessarily the largest volume, but it has the highest voltage somewhat. Oh, because it has the highest capacity. Yeah, wait. So they're all 220. And the rated power is all 300. So I guess it's also depending on the specifics of the circuit. So let's go back to dashboard. So battery 2, it has so something about this arrangement here. They're all because these are number of modules in parallel, which means they have the same voltage. So these are 4 and 5 are the biggest batteries because they have more modules. I mean, they have the number of cells. So 4 and 5, go to summary of results. They're not the highest voltage. Number 4 is the highest voltage. So this combination gives you the highest voltage. Let's go back here and try to get a higher voltage here as well. So let's go with battery 1. So it has the lowest cell number of cells in parallel. It has a number similar amounts of rows. I mean, this is basically columns. You can think of this as the number of columns of your pack, the number of rows of your pack. Okay. Yeah, so it's basically because it has less cells in parallel, that results in a higher voltage. Okay, that's the electrical engineering of it. So let's go here then. Let's vary this. Let's go with all because we're trying to, yeah, let's just keep the cells. Let's say these are all 20. Let's say these are all 12, sorry. 12, 12, 12. Control Shift R to calculate that. It calculates it pretty fast, but just in case, just to keep it all happy. Then let's say this one will be something crazy. 1 cell per parallel. 2, 3, 4, 5, 6. I don't know if this will work, but let's see if this is possible. Control Shift R. And let's all keep this at five columns of modules. Five columns, 4 rows, and 1 module per pack. Okay, so we set up this array to everything is the same. The only thing we're changing is a number of cells in parallel. And that should change the voltage. And so we did that. Let's go down and make sure that nothing crazy happened. They're all still green, except for the fact that you have a warning that you might not be able to get a charge, a fast enough charger. So that's warning number 9. It's just a warning, not an error. Okay, so let's go ahead and move on to the summary of results and see what happened with the voltage. So, as expected, if we just say that we only have 1 cell in parallel, what was it? Here's our array here. If we only allow 1 cell in parallel, then it's going to have a higher voltage than if we connect more in parallel. So only 1 in parallel results in a higher voltage drop across the whole thing. So that's what happened. So it seems like for the Rivian, for the capacity of 200 or so, 220 kilowatt hours with a kilowatt rating of 300, you need to have 1 cell in parallel to have a high voltage. Okay, let's go with that. Let's just move on. So it seems battery 1 meets, of course, this is an estimate based on the unknown capacity and power, but it's consistent because the 135 kilowatt hour standard is known, and then we went from there. Okay, so let's go with battery 1. So I think we basically designed it. That's it. I mean, not it, but that is a pretty much, the rest is, okay. Now, another thing, so we're done with the actual design of the pack and the leading up to the pack coming from the cells. Let's just say there's 12 cells in the module. And there's, to get the voltage high, it's the number of cells in parallel. Then these are all similar sizes in the sense that there's 1 cell in parallel, then there's only 5 columns in 4 rows, and only 1 module in the pack. 1 module in parallel. Okay, so that gives you 800 volts. Then let's go down. The next thing is, how many of these batteries do you want to make per year? For the Rivian, 500,000 is a decent number because they're not going to make 500,000 Rivians per year. They're going to make maybe that order of magnitude, like 100,000 or so. And then, you know, you're going to have some spare, some not necessarily, it's not aftermarket, it's the OEM market of spare parts and repairs. So 500,000, let's leave it there for the Rivian. For the Ferrari, it'll probably be 10 times less than that because the Ferrari is a much more of a specialty market. 10,000 or so Ferraris are made, and then you need the spare parts. So Ferrari will probably be 10,000, 10 times less than this. So, but let's leave this for the Rivian. Okay, let's go down, keep these defaults. Yeah, so that's the only thing to change. We have these warnings on the charging, or I'm actually, if we went to battery 1, there's no warning. So that's good. And yeah, so that's the first bullet point. That's the first bullet point was, what is the capacity, power, and voltage of your battery pack? Why? Well, the capacity is based on an extension of the standard pack, 135 kilowatt hours for the standard. We want the max range, so we had a proportion in it increase in the capacity. The power is a typical power, 300 kilowatts for electric vehicles, and you can give more research if needed. Voltage, 800 volts. They reported that it's going to be 800 volt nominal voltage for Rivian. So we made that happen. Battery 1 does that. Okay, so moving on to the next bullet point. What is the cathode chemistry in your battery pack? Why? We chose NMC 811. That corresponds to 0.8 nickel, 0.01 manganese, 0.01 cobalt. So that the reason why that one is because it is a EV, NMC is a viable EV chemistry for batteries, and we want to maximize the nickel and minimize the cobalt. That's why. And another reason is, if you want to go into more details, you can do further parametric studies and change the chemistry. So you can save this and rerun another one, or you can save this and open up a new file to do another analysis with another chemistry. That that would be a very good thing to do. But we for this, we chose our thing. We already have an answer now. You can go beyond that to get more optimization, more analysis, if you want as well. Okay, what are the dimensions of your battery pack? Why? Well, we chose to maximize the voltage, so that means only one in parallel. So let's try to find the dimensions in space. It literally means what is the height, width, and length. So that's found in summary of results, pack size. So all of these battery packs are basically going to be the same size. They're all going to be, what is this, 1.3 meters by 1.9 meters by 10 centimeters high, or 20 centimeters high, or whatever. What is that? Yeah, 20 centimeters high, 17.5 centimeters high. And we chose, that's a rectangle of a certain volume. So 1.3 meters, that's pretty much the length. The upper limit that you can make for this battery is the footprint of the car. The footprint of the car of a Rivian, this definitely falls within it, and it's going to be a cylinder. I mean a rectangle plate. So we're going to have the prismatic cells built into a module, as we talked about in class. That's in the manual. This is the dimensions. It should fit somewhere on the footprint of the Rivian. Fine. 1.3 by 1.9 meters. Yeah, so and it's why it needs to fit the footprint of the Rivian. And then you can either put it on the chassis floor or you can put it in the trunk. This doesn't look like it's going to fit in the trunk. You might find a way to make more columns, more row to play with the dimensions of the rows versus the columns to get a more of a cube rather than this flat flat rectangle plate. But yeah, that's why it needs to fit somewhere on the footprint. So that's the dimensions. What is the energy and power density of your pack? Those are here. So where is it here? Yeah, battery system metrics. That's the whole system. So it's either going to be expressed in terms of volume or weight. These are energy per liter, energy per kilogram. Those are these two. And where's the power reading? Power. I guess metric here. There's a power. Somewhere here. Oops. So here's a power. That's here in the dashboard. So that's here as well. Pack volume. Pack specific energy. So I guess we would have to divide the power we specified, which would be kilowatts battery rated power, 300 kilowatts divided by 888 here. So we'd have to calculate it ourselves. We know the weight of the total pack and we know the rated power. So that would be the energy power density. Charging process parameters. What is the charging process parameters? That is one charge in 60 minutes. This one can do that. Battery one can do that. One charge per 60 minutes. As we just left this default here. You can play with this if you want. And this is built in. We just left it at the default, and you can increase that if you want, or you play with that as well. That's another thing built in to analyze. But we just left it at default, and that's the charging process parameter. Okay, so moving on to the next bullet point. Are there any battery chemistries you evaluated besides the final design? In this case, no. Why not? Because we chose the highest nickel content, and we knew that Rivian in their max pack, they're not going to go with lithium iron phosphate. They're doing that in the standard, but to go into the max pack, they said they're going to use high nickel chemistry batteries. The one we're on now, NMC 811, it's not the only nickel battery, but it's the highest nickel battery in the BatPac spreadsheet. Okay, so that's why. That's why we didn't evaluate any battery chemistries in the final design. Okay, moving on to section 1B. What is your targeted pack production rate? Why? Our targeted pack production rate is 500,000 because Rivian production is about 100,000 or so. We can look up the specific number. And if Rivian production is around 100,000 per year, then the battery should be a multiple above that to supply every new Rivian and then provide an inventory of replacements and spares. So we chose 500 manufactured packs per year. If we were going to choose a Ferrari, then we'll probably have to go maybe 10 times less than that because there's less the market for Ferrari inventory per year is about 10 times less than that. Okay, so the next one, what are your fixed and variable costs? Well, let's go down to the manufacturing cost tab. The fixed and variable costs are, if you all the way to the top is here. This is how you would open the tab by default, but then you go all the way down to calculation of pack costs. This is a very good summary here. Calculation of pack costs for the 7 batteries we analyzed, we created. And what do I do? Calculation of pack costs for the 7 batteries. And the fixed costs are these. This is for battery 1. And if we want to get a true fixed cost, it's this number per pack times 500,000. That would be the fixed cost for 1 year. The variable cost, it's this, 15,530 per pack. Variable cost is per pack. That's the definition of variable cost. It's per part. Fixed cost is for the whole production, for one fixed lump amount. So to find that from here, you multiply by the amount you made in 1 year. So that's the fixed and variable cost. Okay, next bullet point. What are the stages and parameters for your manufacturing packs? That is the stages. That is going down what we talked about in class. The BatPac model. They used to have it here. I don't think it's here anymore. Cost breakdown. No. So it's not here anymore. It was on the previous version. So for this one, just simply go down that diagram we talked about in class and talk about the, just give a quick summary of the coating process, the solvent recovery, the drying, the calendaring, the airlock chambers, which is required to build the cells and to finalize the coating. Then you can fill it with electrolyte. Then you do the cycling to get the solid electrolyte interface going. Then you can finalize the module and build it. So just give a rundown of that summary, because it's a nice exercise to appreciate how batteries are made, how batteries work. So that's what I'm asking for there. Then add the system diagram that we talked about in class. That's going to help you to guide describing each stage of the manufacturing process. Okay, moving on to 1C. This is where kind of the business comes in. For simplicity, assume you have a 5% interest loan from the Department of Energy to build a new battery manufacturing plant and pay for the first year of production. So, okay, what is the cost to manufacture each pack? Well, that is here. Summary manufacturing cost, cell G499 for battery 1. Each pack costs $20,000 per pack for this high nickel battery. And then the next, so that's the cost. Is your manufacturing cost reasonable? Why or why not? Well, the cost of $20,000 per pack is not reasonable. Why not? Because Rivian is only charging $6,000. What is it? Let me go up the PDF here. Rivian is only charging $16,000 to their pre-orders, and that is maybe with profit or not. We're not sure the details of that cost. So it's not reasonable, assuming that Rivian was able to make it happen for $16,000, And that answers the question. So it's not reasonable, but oh well, let's move on. You can try to make it reasonable. If you get good enough, you can play with this and try to find a good cost and good performance. And that will take some nice engineering. You can engineer with this BatPac, but moving on, this price is not reasonable because Rivian is having a similar performance and they're only charging 16,000 right now. Okay. What is the selling price of your proposed battery pack? Why? Well, it's an actual existing pricing strategy. So this has to do with the business case. So it's not reasonable, but it is possible that Rivian's battery pack does cost 20,000 to make, and they are losing money by charging 16,000. That's possible. I don't know if it is true or not, but we talked about in class, Facebook Meta is losing money on their Oculus. It's only $300, which is, they say they subsidize. So they lose money by charging less money for their product. And their goal is to make money somewhere else on that business line, that product stream, or that ecosystem they're trying to build. So it's possible that Rivian is charging $16,000, even though their battery cost, according to the BatPac, is actually $20,000. So you could even argue here that I'm only going to charge 16,000 because that's what Rivian is charging. Or you can say I want to charge 30,000 for my battery to make some profit. And if you charge less money, the selling price is less than your cost, that means your break-even point is infinity. You'll never break even. You'll always lose money. So you have pretty much, if you want to break even, you have to have some profit. Okay, so if let's go back to our actual answer. Battery one is $20,000 per pack. Let's charge 25,000 to Rivian. Okay, so we charged 25,000. That means we made about 5,000 profit. So that means that if we're gonna the cost to manufacture is this, and the next question is, well, how much money did our manufacturing class cost? Well, that's right here. Our manufacturing cost, for the first year of production, our total investment, including the building, the equipment, the building, the launch costs, working capital, beautiful. It spits out a number to build this first 500,000 batteries, including everything to establish the launch of the manufacturing plant, is $9.5 billion. So you need a loan of $9.5 billion to make 500,000 batteries for your first year. So the question is, if you're going to charge 25,000 and get 5,000 in profit from each sale, how much would it take to break even on your $9.5 billion investment? And that's it. You have the total investment, 9.5 billion. You're gonna you choose to a profit margin of 5,000. That's a strategy on the business part. 5,000. You know you're gonna sell 500,000 the first year. Does that reach 9.5 billion, or what time does it take, assuming 500,000 per year sales at $5,000 profit margin? When do you break even on your $9.5 billion total investment? That's all. That's the calculation. The numbers are spit out at you with a lot of decent assumptions that have been developed over the last 6 years or so. And then, okay, so if that's the case, how are you going to repay your loan? The next bullet point, what is the plan to repay your loan? And that's it. That is all the bullet points. Choose one battery, Once you get a certain capacity, power level, and voltage, according to some similar range that either for the Ferrari or the Rivian, then you pretty much have all the answers of the skeleton shell of to answer these questions, which have, and then if you answer these questions, you pretty much developed a business proposal. So just complete that and get some type of manuscript. The only required diagram is this system diagram there, which I like. I mean, I'm requiring that just as a way to help you quickly run down the process. And you can go into as much details as you want. Some details are available, but many of the uh, every detail is not available in the manual. But these are in the manual. The stages and parameters, the bullet point, section 1B, what are the stages and parameters for your manufacturing pack? Those are in the manual. And the system diagram will help you, hopefully guide you for that. But that's it. So please email me with questions. We can Zoom about it if you want. We can email about it if you want. And I'll go ahead and be available as much as I can. Thank you, and email me with further questions.